In this highlight video, we are going to discuss E2 and E1 reactions. We'll start out by comparing substitution and elimination reactions, and we will then go on to discuss elimination reactions in more detail. After you've watched this video, you should be able to contrast the E2 and E1 reaction mechanisms and be able to describe how the different reaction components, like the alkyl halide, the base, and the leaving group and solvent, influence the mechanism of the elimination reaction. Let's put things into perspective. In the last chapter, we talked about the reaction of an alkyl halide and a nucleophile. In this reaction, the nucleophile displaced the leaving group in either a single step or in two steps to generate a substitution product plus the leaving group. So this is the leaving group. Here's the nucleophile. This is the product. Remember, we talked about solvent, and this is a substitution reaction. We're now going to talk about elimination reactions, and these are reactions that include all of the same components. The only difference is that this Y group here that played a nucleophile in a substitution reaction is going to play the role of a base. And so the base is going to remove a proton from what we call the beta position. So the alpha position is the position bearing the functional group, the leaving group. The beta position is the carbon next to that. So we're going to lose a proton on the beta position. We're going to form a pi bond, and we're going to get an alkene as our product, plus the conjugate acid of the base plus the leaving group. So this is the conjugate acid. This is the leaving group. We have an alkene product, and this is an elimination reaction. Like with substitution reactions, there are two mechanisms that we'll discuss for elimination reactions. The first one is the one-step mechanism. We call this the E2. This stands for elimination. What would the 2 be for? Bimolecular. It's a single-step mechanism, and so all in one step, the base is going to react with a proton on a beta carbon. It's going to remove that proton. The electrons in that hydrogen-carbon bond are going to move down to form a pi bond right here. That carbon can't hold any more electrons, and so the leaving group is going to be removed. So if we follow these arrows, we have this CH2 at the top at the beta position. We have a pi bond, and we still have these two methyl groups down here. We then have water. This is our conjugate acid of our base, hydroxide, plus bromide. Because this reaction is bimolecular, the rate law is going to equal the rate constant times the concentration of the alkyl halide times the concentration of the base. So in this case, if we increase or if say we double the concentration of hydroxide, it'll double the rate. If we half the concentration of the alkyl bromide, the rate will be cut in half. So the rate is directly dependent upon both of those concentrations. The reaction coordinate, or reaction energy diagram, so this is the reaction coordinate here. Remember, this is energy going up the y-axis. In general, alkenes are usually slightly higher energy than alkanes because the pi bonds are not as strong as the sigma bonds. So for this single-step reaction, we'll have a single transition state, and we'll have our product over here. Transition state is going to have a lot of bond breaking and bond forming all at the same time. So here's our OH. Let's not put that minus on there yet. It's going to be reacting with this H, so forming a partial bond, breaking the bond to the carbon, forming the double bond between the two carbons, and breaking the bond to the leaving group. So in the transition state, we'll have a partial minus on the hydroxide because it had a full minus as a reactant, and it's neutral in the product. The bromide, the leaving group, will also have a partial minus in the transition state because it is neutral in the reactant and has a full minus charge in the products. The second mechanism is a two-step mechanism, and it's referred to as E1. So this stands for elimination unimolecular. Okay, so let's draw out the mechanism. Just like in the SN1 reaction, in the E1, the first step is loss of our leaving group, or breaking the bond to the bromide. This generates a carbocation intermediate. In the second step is where the base is involved. In this case, we're using water as the base. Base will remove the proton on the beta position. Those electrons will be drawn down towards the carbocation. If we follow those arrows, we generate this alkene. For this, because it's unimolecular, the rate equals K times the concentration of the alkyl halide. All right, so if we double the concentration of the alkyl halide, the reaction will go twice as fast. But what if we change the concentration of the base or change the concentration of the water? Will that affect the rate of the reaction? No, because it's not involved in the rate determining step. Let's draw out the reaction energy diagram. Okay, so we have reaction coordinate here. We have energy over here. Just like before, we're going to have our alkyl halide. I'm just going to use this abbreviation for that. And slightly higher in energy, we're going to get our alkene product. In this reaction, however, there's two steps, so we're going to have two transition states and an intermediate. So here's going to be our intermediate, right? This is our carbocation intermediate. We're going to have a transition state between the alkyl halide and the carbocation, and another transition state between the carbocation and the alkene product. Notice that the first transition state is the highest energy transition state. This tells us that the first step is the rate determining step. Transition state 1, which would be this one here, would look like something like this. All we would be doing in this case is breaking the bond between the carbon and the bromine. So this bond is breaking, generating a minus charge on the bromine and a plus charge on the carbon. In the second transition state, 2, which would be right here, we are going to be breaking the bond between the hydrogen and the carbon and forming the pi bond between the two carbons. And here's our base. That's water. Okay, so we're going to be, we start with water, we pick off a proton, we're going to end up with hydronium ion, we're going to be building up a plus charge on the oxygen. We started with a full plus on this carbon, so we're going to have a partial plus on that carbon partway through. Let's consider how the various reaction components affects which mechanism is the operative one. We will consider the alkyl halide and its substitution. We will look at the base, whether it's strong or weak, the leaving group, and the solvent. Remember, for substitution reactions, the more the alkyl halide became substituted, the slower the reaction took place. But in elimination reactions, in E2 mechanisms, remember this is the single-step mechanism, it is going to get faster as we go from primary to secondary to tertiary. The reason for this has to do with the energy of the transition state. Right? If we have a primary alkyl halide, let's do it. We're going to have to add an extra carbon on here. We're going to be breaking the bond to the leaving group. We're going to be forming the double bond. And we're going to be removing a hydrogen on the beta position. Here's the base. So we usually have a delta minus for a strong base and a delta minus on the H. If we do this for a tertiary alkyl halide, we're going to have something that looks similar here. Delta minus here and delta minus here, but what we've left off is that we would have two additional R groups at this position, at the position where the leaving group was attached. Now remember the relative stability of different alkenes. So the more substituted, or the more carbons that are attached to a carbon-carbon double bond to an alkene, the more stable it becomes. And so the more highly substituted tertiary transition state would be more stable than the less substituted primary transition state. And because a lower energy transition state is going to lead to a faster reaction. Okay, so for E2, tertiary is the fastest. What about for E1? E1 is going to have the same trend. Okay, this is going to go faster as we go to the right. So is it going to be for the same reason? No, the reason here is the same as what we saw for the SN1 reaction, because remember, E1 involves the formation of a carbocation. And so as we go from primary to secondary to tertiary, we are going to generate more stable carbocations. Right? Just because it's a more stable carbocation intermediate doesn't mean that it's faster, but remember that if we apply the Hammett postulate, that allows us to relate the stability of the intermediate to the stability of the transition state. Elimination reactions require a base, and if we use strong bases like hydroxide or alkoxide, this favors E2. Two additional bases that the book shows, these are a little bit complicated, but what we really want in the base here is it'll act as a base but not as a nucleophile. So that slows down any competing substitution reaction. This is referred to as DBN. We won't worry about the full name. You can look that up in the text. And another one that's related, the 7-membered ring and a 6-membered ring. Oops, this is an N up here. This is called DBU. The way that these species, these bases, react with protons is that these electrons go to form a pi bond here, and this pi bond is the position of protonation. Weak bases, in contrast, favor E1. So again, weak bases here are going to be things like water and alcohols. For leaving groups, better leaving groups are going to favor E2 slightly over E1, even though good leaving groups will speed up the rate of both mechanisms. So remember, as we go from chlorine or chloride to bromide to iodide, this is going to get faster and favor E2. For solvents, just like for substitution, the single-step mechanism is favored by aprotic solvents like DMF, DMSO, acetone, and E1 mechanisms are favored by protic solvents like water and alcohols. Notice that the solvents for the E1 mechanism are the same as the bases for E1 mechanisms. Okay? And so this is where we get this kind of solvolysis reactions, where the reactant, where the base, or the nucleophile for SN1 is also the solvent. Let's summarize. For the E2 mechanism, second order, that's what the 2 means. Second order reaction is a single step. It's concerted. All of the bond breaking and bond forming take place simultaneously. For the R group on the alkyl halide, the more substituted alkyl halides, tertiary over here, react faster than primary. So the more substituted alkyl halides react faster. This is the reverse of SN2. SN or E2 is favored by strong bases, better leaving groups, and polar aprotic solvents. For E1 mechanisms, it's first order, and that's what the 1 stands for, though it contains 2 steps, where it includes a carbocation intermediate. The more substituted the alkyl halide, the faster the reaction, and that's also because of the formation of the carbocation. Remember, more highly substituted carbocations are more stable than less substituted carbocations. It's favored by weak bases, good leaving groups, and polar protic solvents.